Hey everybody, sorry about that small snafu. Hopefully if you were part of the chat, you saw that I was working through my technical difficulties, but hey, I'm here, I'm live, I'm on. Nice to be with you all. My name is Dr. English and I am going to be talking about acid, bases, and neutralization reactions. And to help me with this broadcast today, I have the one, the only Rob Collard. Say hello, Rob. That's Rob Collard from Grand Island High School. That's right. So anyways, got a lot to talk about today. Mr. Collard is going to be on the chat. So if I don't respond to your question right away, hey, that's all right. Mr. Collard is here to help. So let us share our screen and get going, shall we? Share. Yeah, that's nice. Play. All right, acid-base chemistry. Need to go over one. Okay, what are we doing today? We're going to be talking about what to expect from this. We're going to talk about acids and bases as electrolytes. We're going to do the Arrhenius definition of acids, talk about naming acids, reactions between acids and metals, Arrhenius definition of bases, and then we're going to talk about some characteristic properties of bases, the nature of the hydroxide ion, and then, of course, everybody's favorite, the alternative acid-base theory. Some neutralization reactions, the ionization constant for water, which you think, well, I don't really need to know about that, but actually, not a bad thing to know. The pH scale, of course, acid-base indicators, and finally, bringing it home, some acid-base titrations. And during this whole thing, we will have Regents questions linked to each of the topics. So sit back, relax, enjoy. I did connect my slides for this presentation at the bottom of my screen. So if you need those, well, hey, they're there. What to expect from this review? Quick review of acid-base content. Again, we're going to do some worked Regents chemistry questions, which if you've ever been to my site before, you know how we do this. You should have your chemistry reference tables, of course, because why wouldn't you? The acid-base review notes, and of course, a calculator is always helpful. So let's get started, people. Reference tables, of course. Okay, acid and bases as electrolytes. So we've got some aqueous solutions of acids and bases will conduct an electric current. Let me get my pen going here. And are considered electrolytes. They are considered electrolytes. Remember, an electrolyte is a substance that can conduct an electric current when dissolved in water. And now we've got this little simulation right here. So we've got a light bulb, a battery, and then two electrodes. And we're going to be starting off in water. So if I put my two electrodes in the water, you see, okay, light bulbs are really not going on. If I go to a strong acid where I have a lot of ions, hey, look, that's a really strong reaction. It's really conducting electricity. Same thing, we'll see that in a strong base. Okay, so as long as there's ions in solution, which we know are charged particles, they will conduct an electric current. Water, not so much. And I'm not going to go into the weak and strong acids here at all. All right. The Swedish chemist Svante Arrhenius investigated the nature of electrolytes, in other words, substances that conducted electricity when dissolved in water in the late 1800s. Arrhenius determined that electrolytes ionize when they dissolve in water. This means that electrolytes separate into positive and negative ions, which of course we know as charged particles. These ions are free to move in the resulting solutions. The ability of a solution to conduct an electric current is dependent on the concentration of ions. Now, when you see that word concentration, you, of course, should be thinking molarity, and the molarity formula is on table T of your reference table. Strong acids and bases are good conductors of electricity because they will ionize or break down into their component ions. So here's two prime examples. Hydrogen chloride as a liquid. Notice, I'm not saying hydrochloric acid. It's got to be in an aqueous solution to be hydrochloric acid. So hydrogen chloride as a liquid, when we put it into water, it's going to fully ionize into hydrogen ions and chloride ions. That's why we see the little AQ right there. Same thing for sodium hydroxide, except we call this dissociate. But sodium hydroxide usually comes in these little white pellets. We add that to water, and it's going to break down into sodium ions and hydroxide ions. Yeah, table T, yay. All right, so let's get to some sample Regents questions. Now, based on what I've seen the other teachers who have been doing these reviews, they've been using Remind, which is great, and that's awesome, but I can't see responses. So I'm just going to go through these questions, and I'm going to point out which ones are right, which ones are wrong, why those are correct, why those are incorrect, and maybe you can work them out on your own as you go through them. All right, which two compounds are electrolytes? Now remember, if it's an electrolyte, it's got to be able to break down into charged particles. So I look at the first one and I think, all right, KOH. Well, that's potassium hydroxide. That's a strong base, and we know that's going to dissociate. So that's an electrolyte. Then we get to CH3COOH, and we know that that is, according to reference table K, you can call it one of two ways, ethanoic acid, acetic acid, but it is an acid. So because potassium hydroxide is a base and acetic acid is, well, you know, an acid, this is ultimately going to be our correct answer. But you should be one of those students that takes the time, because you're going to have more than enough time on this exam, to read through all the questions before you make your choice. It just happened that this one was the correct answer. So why is the second one not correct? Well, we see KOH again. Okay, that's a base, so that would be an electrolyte. But C5H12, yeah, that's pentane. That's a hydrocarbon. Let's put HC, hydrocarbon. That is so not an electrolyte. Definitely not an electrolyte. It's not going to ionize. It's not going to dissociate. It's not going to form charged particles, and we'll talk about that more in the future. CH3OH, that is methanol, an alcohol, also an organic compound, not going to ionize, and again, we'll talk about that in the future of why that happens. CH3COOH, that's an acid that would. Here's methanol again, which makes number 4 not a possibility. And oh, look, pentane. So it's non-electrolyte, non-electrolyte. That's why choice number 1 is the preferred choice. All right, which substance is an electrolyte? And just so you know, all the questions that I'm going over today is basically every single multiple choice question from 2008 until the present. So if you're like, well, Dr. English, those two questions totally repeated themselves. I know, because that happens all the time on the Regents exam. So for the first one, C6H12O6, that's glucose. That is not an electrolyte. C2H5OH, that's, let's see, that's ethanol. Also an organic substance, and alcohol, not an electrolyte. NaOH, hey, that's a strong base. We know that's going to break down into ions. That is going to be our correct answer. And H2, yeah, H2 is a diatomic gas, not an electrolyte. There is no way under normal circumstances that's going to break down into 2 hydrogen atoms. And oh, look, which compound is an electrolyte? I know you might be saying to yourself, wow, we're repeating ourselves again. It's true. CH3CHO. I like this one. This one's a great question, though, because you need to recognize that this thing right here is an aldehyde. This HO, aldehyde. CH3OCH. I think that's an ether. Mr. Collard, am I right? Is that an ether? That's an ether, isn't it? It's been a while. I think that's an ether. Anyways, that is definitely not an electrolyte. So I'm going to say ether. Oh, look, CH3COOH. We're going to have our Q group, which is going to be our acid. So that is the correct choice for the electrolyte. And CH3CH2CH3, well, that's a condensed structural formula for propane. So not an electrolyte. So really, for a lot of these answers, all the substances that are correct either show up on either table K or table L. So good to be able to know that. All right, Arrhenius acids. Since acids are electrolytes, they must ionize in water, which we know is break apart into positive and negative ions. Arrhenius observed that when acids ionize, they all form the hydrogen ion, H+1, as the only positive ion. So let's look at an example, shall we? HBr. Hydrobromic acid will ionize or break down into its ions in the following manner. I've got hydrogen bromide as a liquid. I add it to water, and all of a sudden I have hydrogen ions and I have bromide ions. Let's look at another strong acid, HNO3. Oh, and that AQ shouldn't be there. It should just be hydrogen nitrate. Not until we add it to water does it become an acid. So when that breaks down, we're going to have hydrogen ions, and we're going to have the nitrate ions. So again, these are all Arrhenius acids because we see that hydrogen ion in solution. That is what you're looking for in terms of an Arrhenius acid. All right, now, not all substances that contain hydrogen are acids. Organic molecules such as methane, which is CH4, they do not ionize and therefore are not electrolytes nor acids. There exists a class of acids known as organic acids that yield hydrogen when they dissociate. And the classic one that you're going to see over and over and over again on the exam is our good friend ethanoic acid, also known as acetic acid, also known as vinegar. So here is our ethanoic acid, and it's going to be dissolved in water, and we're going to form the hydrogen ions again, and we're going to form that acetate ions. Now, the key thing to remember here is that this is what we call an acidified hydrogen. Okay, this is the hydrogen right here that's going to basically ionize from this compound. Not these hydrogens right here. The carbon is holding on too strongly, okay? There's not a big enough difference in electronegativity for those hydrogens to come off. It's only this hydrogen right here that will be released in solution to say, hi, I'm an acid. So that's what we're looking for. So the nature of the hydrogen ion. Since the hydrogen atom consists of one proton and one electron, the hydrogen ion is a proton. Now you might be saying, well, Dr. English, what do you mean by that? All right, so here's a proton. There's my proton. And then we've got that so-called first shell. And then we have our electron in that outermost shell. And that is my hydrogen atom. Okay, one proton, one electron, everything's neutral, it's all good. But if that electron suddenly goes away, all I have is, a proton. So a proton is H+1. It's the hydrogen ion. So many chemists believe that a proton cannot exist alone in an aqueous solution. These chemists believe that the proton forms a coordinate covalent bond with a water molecule to form the hydronium ion, H3O plus 1. Now, let's understand something. There's a good possibility that you've never heard of coordinate covalent bonds before. Don't panic. It's really okay. You're not going to see it on the exam. But in my world, understanding what a coordinate covalent bond is and why the hydronium ion can exist is, insanely important. So table E gives you the hydronium ion. So let's take a moment here, people. Let's take a moment and let's draw the water molecule. Here it is. And most importantly, it's got two lone pairs. Lone pairs. There they are. Okay, so there's my lone pairs. Now, here is my hydrogen ion. And my hydrogen ion, it'd rather be stable. Yeah, this hydrogen ion would rather be stable. We've already ripped away one electron. It's just a proton. And we know in terms of stability, it would really like, if we, give it human characteristics, it would really like two electrons. So what it's able to do is to go over to one of these lone pairs and snuggle up to one of them and say, hey, that's comfortable. I'm going to stay here. And as a result, we get this. We get the O, hydrogen, still have our lone pairs. There's our lone pairs. But now I've got my hydrogen up here saying, look, you're sharing your two electrons with me. You're sharing your lone pair. But I still carry a charge with me. And that charge is +1. And that, ladies and gentlemen, is how you form a hydronium ion. That's how this can exist. So, FYI. An acid can also be defined as a substance that ionizes in water to produce the hydronium ion as the only positive ion. So that's the connection between the last slide, because the words hydrogen ion and hydronium ions are used simultaneously. So the ionization of hydrochloric acid in water can be written in two different ways. We can have HCl in liquid and put it in water and say, oh, look, there's a hydrogen ion, and here's a chloride ion, and it's all good. So in this example, water is not included but assumed. The hydrogen ion is formed and indicates the presence of an acid. That's all good. The chloride ion is also represented as another product. But let's look at this next equation right here. In this example, the water is included in the equation to show how the hydronium ion is formed. The chloride ion is also represented as another product. So here's my HCl. My HCl is going to ionize. It's going to break into these two products over here. The hydrogen is like, I'm all alone, I need help. So it goes over to the water molecule and it forms that coordinate covalent bond, and oh look, there's the hydronium, and here's the chlorine, which becomes the chloride ion as a spectator ion, and yeah. So both of these are exactly the same. It's just demonstrating that on the exam, they can use hydrogen ions and hydronium ions at the exact same time. And yeah, they could test you on that. Therefore, hey, look, I just said this. The hydrogen ion and the hydronium ion are essentially the same and both indicate the presence of an acid in an aqueous solution. Polyprotic acids, poly meaning many, protic meaning protons. So some acids are able to produce more than one hydrogen ion when they ionize. Sulfuric acid, H2SO4, has the potential, and I stress potential here for all of you honors chemistry students out there, to ionize and ultimately produce two hydrogen ions. So technically, we can have H2SO4 going into water, and we form the hydrogen ion, so there's one, and this hydrogen sulfate ion. But to a lesser degree, the hydrogen sulfate ion can also lose this hydrogen and release it in water. So it's the hydrogen ion again and the sulfate ion. That's why it's considered polyprotic, because in very general terms, you could get hydrogens out, two hydrogens out of this H2SO4. Naming Arrhenius acids. This is great. What do you need to do? You need to go to Table K. So the formulas of an acids can be recognized because they begin with the element hydrogen. Of course, our organic acids are the exception. So for the most part on the exam, if it's an acid, it's gonna be here. I'm not lying. This is it. This is where it's gonna be. If it's not here, then they've got to give the name and the formula. But for the most part, don't guess. Go to Table K. Let's go back to the organic acids again, and that is going to be down here. Remember, these can be identified because these acids end with the COO group, the COOH. So it's this part right here, and as we said before, this is our acidified hydrogen. That is the one that's being removed, not these ones down here. These are all staying. They're not being released. There's too small of a difference in electronegativities for the carbon and the hydrogen for between those two for that to ionize. All right. Hey, look, we're at some more questions. So let's take a look. Let's see what we can do. Which type of substance yields hydrogen ions, H+, in an aqueous solution? If you said number 1, you're right. So an Arrhenius acid, definitely not a base, a saturated hydrocarbon, an unsaturated hydrocarbon. A lot of time with these questions, they're going to come back to hydrocarbons because they're going to try to trip you up with the organic acid. Which compound yields hydrogen ions as the only positive ion in the aqueous solution? All right, let's start from the top. KOH, that's a base, out. NaOH, that's a chemical salt. Okay, we've got the sodium ion, we got the hydroxide ion. That's not going to give us a hydrogen ion. Here's the distractor right here, CH3OH, that is methanol. That's an organic compound. You're not going to lose that hydrogen. You should recognize what that is. And oh, look, the correct answer right here, yay. CH3COOH, again, on Table K, it is an acid. This is the hydrogen that's going to be released. All right, let's go on to the next one. Which compound yields hydrogen ions as the only positive ions in the aqueous solution? And I know you're looking at your screen and you're thinking, she's asking the same question over and over again. I know, but again, these are the questions that have shown up since 2008. These are the ones you need to be able to understand how to do. So I digress. Hydrogen ion is the only positive ion. All right, H2CO3. If I looked that up in my reference table, I would know that is carbonic acid. So that's a possibility. And HC2H3O2, that's the inorganic way of saying acetic acid. So this is our correct answer, but let's go and look at why the others are not. We've got carbonic acid again, but now we have sodium hydrogen carbonate. This is a chemical salt. I'm just going to put CS, chemical salt, because when this breaks down, when this dissolves in water, it's going to form sodium ions and hydrogen carbonate ions. It's an electrolyte. Don't get me wrong, it's an electrolyte, but it's not going to release hydrogen ion solution. NH3 is going to be a base, and we're going to talk at length of why that is later. HC2A, okay, that's an acid, base, and again, a chemical salt. So number one is the only answer that actually makes sense. Hey, look, there's more. Substance that dissolves in water and produces hydronium ions. Hydronium ion is the only positive ion in the solution is classified as a, well, we know the hydrogen ions and hydronium ions are the exact same thing, just how you write them and what you consider about stability. So this answer has to be 2, acid. Which substance yields hydrogen ions as the only positive ion in the aqueous solution? Again, they like using the aldehyde because they're trying to trip you up because they're expecting that you're not going to know how to read that. This one is an alcohol. This one is my acid. That's going to be my correct answer. And this one, again, is an ether. So 3 is my answer. Because look at, these all are, these are all organic compounds. You need to be able to differentiate between these and say, I know what I'm looking for here. I'm looking for the organic acid. And you go to your reference tables to do that. What can be explained by the Arrhenius theory? If you chose number 1, the behavior of many acids and bases, you, person, are correct. All right, let's move on. Reactions between acids and metals. Oh, look, it's table J. One of the properties of acids is that acids will react with certain metals to produce hydrogen gas. So let's get an example here. Magnesium metal reacts with hydrochloric acid to produce magnesium chloride and hydrogen gas. And if we put this out into our equation, it would be solid magnesium. There's our 2HCl yields, magnesium chloride, aqueous, and hydrogen gas. So what's happening here? Well, the magnesium is right here. And this is our hydrogen standard down here. We know, based on what you have learned in chemistry, that any metal above that hydrogen can replace that hydrogen if that hydrogen is in a compound. So that is why magnesium can react with the HCl and kick the hydrogen out. Any metal below will not. So again, this is basically a single replacement reaction. The magnesium comes in. It says you're out. The hydrogen is going to go over here. It's going to form its most stable form of the hydrogen gas. And then the magnesium is going to hook up with the chloride, with the chlorine and form magnesium chloride, which we really know are represented by ions. But hey, we're keeping it simple here. Which element reacts spontaneously with 1 molar HCl at room temperature? So let's take a look at the elements that they list. They list copper, that's here. They list gold, that's here. Silver, that's here. And zinc. Hey, which one doesn't belong? That would be the zinc, because the zinc is above the hydrogen. The zinc can replace the hydrogen. Everything else is below the hydrogen. Not an option. Not an option. All right. So again, metals on table J, which are above H2, will react with 1 molar acid. Well, those below will not react. So an example is copper is located below the hydrogen on table J. We basically already said this. So if you think, oh, copper wants to come in and kick out the hydrogen, no reaction. That's not going to happen. So be careful about that. All right. Other properties of Arrhenius acids. Dilute solutions of acids will have a sour taste. So the sour taste of oranges and lemons is due to the presence of citric acid. Vinegar, like I've stated before, has acetic acid. Tea contains tannic acid. Look at that crazy formula. That's awesome. Coke and Pepsi contain phosphoric acid. So that sour taste, because of acids. Hey, look, we're finally talking about bases. But specifically, we're going to talk about the Arrhenius definition of a base. So the formulas and names of some common bases are given on table L. An electrolyte that yields hydroxide ions, OH-1, which remember is on table E, as the only negative ion in aqueous solution. So here's table L, common bases, sodium hydroxide, potassium, calcium, and aqueous ammonia. And again, we'll talk about why that's listed there in a little bit. Commonly found as ionic compounds between metals from group 1 and some of group 2. So here's an example. Sodium hydroxide will dissociate in water to form sodium and hydroxide ions, as we see down here. Classic properties of bases. Bases feel slippery or soapy. They tend to taste bitter, react with oils and fats, and are commonly found in household cleaners, as we see down here. Just some general properties of bases. Now, the nature of the hydroxide ion. The presence of the hydroxide ion results in bases having their characteristic properties. Alcohols are organic compounds that contain the OH or hydroxyl group, but are not bases, so not a base. Alcohols do not ionize in water to yield the hydroxide ion and thus are not electrolytes. Alcohols can be easily recognized by the fact that they begin with the element carbon. So look, methanol, we've been using this example all during this presentation. Methanol is CH3OH. When you put it in water, it's still CH3OH. And if you saw the presentation on intermolecular forces and things like that, that should make sense to you. And I'm not going to get into, I am so not getting into that right now. Definitely not. But methanol will not break down. You will not see this hydroxide ion released out into solution. So let's look at two examples. Actually more than two. The compound NaOH solid is dissolved in water to yield hydroxide ions as the only negative ions, hydroxide as positive, hydronium as negative, hydronium as positive. This is a classic question of reading too fast. If you read this question too fast, you are easily distracted by 3 and 4, which talk about hydronium ions, which we know are hydrogens, which are acids. So 3 and 4 are out. All we need to know is that hydroxide, when it breaks down, will form OH-1 because Na has a positive charge associated with it. So the correct answer for this one is going to be 1. Hydroxide ions as the only negative ions. Strontium hydroxide is classified as a Arrhenius base because SrOH2 contains, all right, well, let's take a moment here. We've got SrOH2. That's going to break down into strontium ions, Sr plus 2, and hydroxide ions, OH minus 1. And for you purists out there, I'll put the 2 in front of here because there's 2 here, so it balances. But when this breaks down, we have our hydroxide ions. So choice 1 is our correct answer for that one. Which compounds are classified as Arrhenius bases? Again, I would depend heavily on table K and table L to solve this one because I think for the most part, they're all on there. HCl is an acid, so number 1 is out. That is an acid. HNO3 is an acid, and NaCl is a chemical salt, and of course, NaOH, of course, is a base. We need both of these to be a base, though. NH3 is a base, according to table L, and H2CO3 is carbonic acid, so 2 and 3 are out, which leaves us with 4. Calcium hydroxide and potassium hydroxide. When these two are dissolved in water, they will dissociate to form hydroxide ions. Which compound releases hydroxide ions in aqueous solutions? All right, number 3 is out. That's an acid. Okay, CH3OH, they're going to use that for you as a distractor because you're going to look at the OH and think, oh, that's a base, but really it's not. It's methanol. That's out. Be careful of one. We look at this and we know it's an acid because we see that Cu group, but I guarantee some people will get distracted and look at that OH and be like, oh, that's where my OH is coming from. No, you are wrong. No, that is COOH. That is an acid. That one is out. It is the KOH, the potassium hydroxide, which is going to be the correct answer for that one. How are we doing, Mr. Collard? Any questions out there from the group? Are we doing okay?
I don't see any questions. Nobody's questioning.
All right. That's all right. Alternative acid-base sharing, or alternative acid-base theories. The Arrhenius definitions of acids and bases is limited to aqueous solutions only, which means water solutions. Acids and bases do occur outside of aqueous situations, so alternative acid-base theories exist. One theory states that an acid is a hydrogen ion donor and a base is a hydrogen ion acceptor. This is called the Bronsted-Lowry acid-base theory, and if you've never heard it before, that's really okay. A lot of chemistry teachers will just refer to it as an alternative acid-base theory. Now, the easy thing is that all Arrhenius acids are hydrogen ion donors, okay? They're all going to release hydrogen ions. So I can look at HCl and say, oh, that's an acid because it's when it's dissolved in water, we get hydrogen ions. Or here, oh, look, it's nitric acid or hydrogen nitrate. When we put that in water, that's going to donate hydrogen. So Arrhenius acids are always Bronsted-Lowry acids. They are always hydrogen ion donors. Mr. Collard, do we have a question from the crowd? No. No questions.
Keep going.
All right. The Bronsted-Lowry acid-base theory defines a base, however, as any substance that accepts a proton, and this is key. So again, a hydrogen ion. This definition expands the number of substances that are considered bases beyond what is included in the Arrhenius definition. A base that accepts a hydrogen must have a lone pair so that a coordinate covalent bond can form between the accepted hydrogen ion and the base. And this is why, ladies and gentlemen, ammonia, NH3, is considered a base under this alternative theory. Now, you might say, well, I need to see that. Well, let's look at ammonia. All right, so here's nitrogen. That's a funky looking N. H, and we have a lone pair. Okay, and then here's my hydrogen ion. Okay, here. So ammonia is considered a base because this hydrogen has the ability to come over to this lone pair and form the ammonium ion. So we're going to have, again, our nitrogen, hydrogen, lone pair, and then that hydrogen will come in on the top, and we're going to form that ammonium. Okay, but this is considered a base, again, because it has that lone pair. That is why it's considered a base. The other example that you might see on the exam is water, and we see this quite a bit. So here's my water molecule. Okay, I've got a lone pair and a lone pair right here, and here comes my hydrogen ion. Here it comes. Okay, water can act as a base because this hydrogen ion can come over here and form that coordinate covalent bond. So when we rewrite this, we've got OH, lone pair. We've got the hydrogen, and we've got an overall charge of +1. Okay, so this is water acting as a base because it can accept that hydrogen ion. And oh, look, we just formed, hydronium. Just formed hydronium. All right, so let's look at some examples. Which statement describes one acid-base theory? An acid is a hydrogen ion acceptor, and a base is a hydrogen ion donor. An acid is a hydrogen ion donor, and a base is a hydrogen ion acceptor. That's going to be our correct answer here because we know an acid will give up a hydrogen ion and a base will accept one. This was a weird question that I found, but they actually made, well, I'm going to tell you right now, 3 and 4 are most definitely out. And they made the hydrogen ion as a negative ion. And, hydrogen can be negative. It can. when it forms a bond with like a group 1 or a group 2 metal, and it forms a metal hydride. But when, you know, this would be hydrogen as a positive ion. So the correct answer for this one is 2. According to one acid-base theory, excuse me, the water molecule acts as an acid when the molecule, it's going to be donates a hydrogen ion. And you might say, well, I saw water acting as a base. What do you mean what could act as, you know, it could act as an acid? Okay, well, here is my water molecule again. And we're going to find out that this water molecule can basically break down, ionize, lose one of these hydrogen ions, and we get our hydrogen ion, and we get our hydroxide ion. And this is going to come into play very soon when we talk about pH. So this is water acting as an acid when it gives up this hydrogen ion. All right, another question. According to one acid-base theory, NH3 acts as a base when an NH3 molecule, and the correct answer here is going to be accepts a hydrogen ion. We've been over this because remember, if it's a base, it's got to accept a hydrogen ion. It does not have anything to do with the hydroxide ions. Given the balanced equation representing a reaction, we have water, hydrochloric acid, we have our hydronium ion and the chloride ion. According to one acid-base theory, the water molecule well, what is the water molecule doing here? My water molecule is basically going to accept. It is going to accept a hydrogen ion because we've got an acid right here. Okay, so this hydrogen is going to be donated, and it's going to be given over to the water molecule. And when it gives over to the water molecule, it's going to form that hydronium ion right there, and again, that spectator chloride ion. So that's where the water is going to accept the hydrogen ion. Oh, look, it's a fancy diagram. Given the diagram representing a reaction, and these are quite common now in the Regents exam, we've got basically the exact same question as we did before, but definitely represented a little differently. So we have HCl, water, hydronium, and chloride. So according to one acid-base theory, the water acts as and again, as we saw in the previous question, a base because it accepts a hydrogen ion. So it's the hydrogen going over to the water molecule and forming that. It's accepted it, we form the hydronium ion. And then finally, the last one, according to one acid-base theory, a base is a hydrogen ion acceptor. Okay, and again, always use table L as your reference. They're gonna use ammonia as a classic example of a Bronsted-Lowry base. Let's talk about neutralization reactions really quick. Acids react with bases to form water and a chemical salt. Neutralization reactions are a type of double replacement reaction. So hydrochloric acid reacts with sodium hydroxide to form water and sodium chloride. That is our chemical salt right there, and we can see that represented. This reaction is called a neutralization because the hydrogen ion of the acid combines with the hydroxide ion of the base to form water, which is pH neutral. So there's two ways of representing it. You could just do it the quick and dirty, H+1, OH-, giving us the water, or we can do it more stable format with the hydronium and the hydroxide, forming water molecules over on the other side. Another example could be something like potassium hydroxide and sulfuric acid. The hydroxide and the hydrogens are going to get together and they're going to form water. And then the potassium and the sulfate from here are going to get together and they're going to form potassium sulfate, which is a chemical salt. Chemical salt, remember, is a neutral ionic compound that is a product of neutralization. A product of neutralization. So let's look at some questions, shall we? Which word equation represents a neutralization reaction? If you said acid plus base gives you salt and water, you are correct. All the other answers here are just a mashup of these four things put in the wrong order. So we need acid plus base, salt, and water. What are the products when potassium hydroxide reacts with hydrochloric acid? This looks a little disconcerting, not going to lie. So what I would do is I'd say, all right, KOH, I'm going to react that with hydrochloric acid, and I'm going to see what happens. We know that one of the products here is going to be water. So over here, I'm going to write H2O. And then I'm going to look at my other two things that are left over. the potassium, all right, K plus 1, and the Cl, which is Cl minus 1. And I know when I write this formula, it's going to be KCl because that's what they want us to say in our answer. So the correct answer here is KCl aqueous and H2O liquid. So this is just a simple double replacement reaction. Just make sure that the water is one of your products. All right, let's look at another one. Which solution reacts with LiOH to produce a salt and water? All right, LiOH is a base. I'm looking for an acid. KCl is a salt. KAO is a salt. Sodium hydroxide, well, that's another base. So I need H2SO4, which is on my list on table K of common acids. So my correct answer here is H2SO4. Which salt is produced when sulfuric acid and calcium hydroxide react completely? All right, let's take a moment. H2SO4 and then calcium hydroxide, CaOH2. Again, one of my products is always going to be water, so H2O. And then I have my Ca from right here. That's +2. That's a really sad +2. And my SO4, which is -2. The +2 and the -2 are going to cancel each other out. So my salt is CaSO4. That is my chemical salt. And that correct answer is 4. All right, ionization constant for water. Although the water molecule is not ionic, it is able to ionize to a very small extent. Water ionizes in the following manner. Liquid water is going to break down into hydrogen and a hydroxide, or hydronium and hydroxide, again, depending on how you do it. This means any water solution is going to contain both hydrogen and hydroxide ions in it. The product of these two concentrations is equal to a constant, and that constant can be expressed by this, Kw, hydrogen ion concentration, hydroxide ion concentration, and it's equal to 1 × 10⁻14. Remember, your brackets signify concentration, which we know as molarity. Now, you might say, well, Dr. English, where is this going? If the concentration of the hydrogen ions increases, the concentration of the hydroxide ions must decrease because again, we're dealing with a constant. So if one goes up, the other one's got to go down. So if the concentration of the hydrogen ion decreases, the concentration of the hydroxide ion has got to go up. It's got to increase. So in pure water, the hydrogen ion and hydroxide ion concentrations are relatively equal. In other words, we know as neutral pH. So the hydrogen ion concentration is 1 × 10⁻7, and the hydroxide ion concentration is also going to be 1 × 10⁻7, because we know if we multiply these two things together, we're going to add the exponents and get 14. And that's sort of important. All right, in an acidic solution, the hydrogen ion concentration is greater than the hydroxide ion concentration. There's going to be more hydrogen ions than hydroxide. In a basic solution, the hydroxide ion concentration is going to be greater than the hydrogen ion concentration. So more hydroxide than hydrogen. Which leads us to the pH scale. And remember, pH just means potential of hydrogen. That's what the P stands for, if you never knew. Potential of hydrogen. So the pH of a solution can be related to its hydrogen ion concentration by the equation hydrogen ion concentration is equal 1 × 10⁻⁻⁴ pH. A solution with a hydrogen ion concentration equal to 1 × 10⁻⁸ has a pH of 8. So something that is 1 × 10⁻⁴ has a pH of 4, 1 × 10⁻11 has a pH of 11, and 1 × 10⁻9 is going to have a pH of 9. So here we have a little simulation, and we have our pH meter right here, and we're starting off at water. So if I put the pH meter in water, we have a pH of 7. If I take it over to a strong acid, my pH is now 2. It's going to go down. And then if I go to a strong base where there's more hydroxide ions, my pH is going to go way up and be a pH of 12. The strength of an acidic or basic solution is a function of its hydrogen ion concentration, not hydroxide, hydrogen ion concentration. The concentration of the hydrogen ion can be expressed using a scale called pH. Neutral solution has a pH of 7. Acidic solution has a pH of less than 7. And the smaller the pH, the more acidic the solution. Finally, basic solutions have a pH greater than 7. So the greater the pH, the more basic the solution, the smaller the amount of hydrogen ions. Since pH is an exponential function, when the pH changes by 1 unit, the hydrogen ion concentration has changed by a factor of 10. So a solution of pH 1 is not twice as acidic as a pH of 2, it's 10 times as acidic. A solution of a pH of 1 is not 3 times as acidic as a pH of 3, it's 100 times as acidic. So every time you move a space here, it's times 10. So a pH of 9 is 10 times more basic than a pH of 8. A pH of 9 is 100 times more basic than a pH of 7 because, again, 1, 2, each of these things is times 10. And a pH of 9 is 1,000 times more basic than a pH of 6 because there's 3 units separating the two. So let's look at a bunch of questions. Yeah, let's look at a bunch of questions. All right. When the pH of a solution is changed from 4 to 3, it's changing 1 unit. The hydronium ion concentration. Okay, so it's going from 4 to 3. That's more acidic. So if it's becoming more acidic, the hydronium ion concentration has to increase. And since it's only going 1 unit, it's going to increase by a factor of 10. The pH of a solution is 7. When acid is added, so we're adding hydronium ions to the solution, the hydronium ion concentration becomes 100 times greater. So we're becoming more acidic. We'd expect that our pH is going to go down. And if it's 100 times greater, that's 10 times 10. So that's moving 2 units, which means if it's 7, it's going to become more acidic. So we got to go over 2 spots to 5. When the pH of a aqueous solution is changed from 1 to 2, the concentration of the hydronium ions in the solution, all right, 1 to 2, that's basic. That's basic. So, and it's moving 1 unit. So my hydronium ion concentration, which is the concentration of hydrogen ions, how acidic it is going to decrease. It's going to go down because we're becoming more basic. Decrease by a factor of 10 because we're only moving 1 unit. Some more examples. When the hydronium ion concentration of a solution is increased, we're becoming more acidic by a factor of 10, the pH value of the solution is going to decrease by 1 pH unit, okay, because we're adding more hydronium and it's acidic. When the pH value of a solution is changed from 2 to 1, again, we're becoming more acidic. The concentration of the hydronium ions is going to increase by a factor of 10 because remember, we're going from 2 to 1, which is more acidic, and every time you move one of these units, that is times 10. And these are some of the more difficult questions on acids and bases in the on the exam. Indicators, really quick. Substances that change color when exposed to solutions of different pH values. Table M lists several indicators, the pH range at which they change, and the color change they undergo. By testing a solution of unknown pH with more than one indicator, it's possible to determine the pH of the solution. All right, so here we have our last simulation. I have a piece of litmus paper and I'm going to put it in water. And when I put that piece of litmus paper in water, I can see that it's yellow. I match it up. Hey, it's around 7. If I switch this over to a weak acid, I don't know, I guess I felt like doing a weak acid. I do this and I'd say, you're about a 4. So that's becoming more acidic. We can see that. Strong acid would be much farther down here. And look, it's red, so it's much farther down. That indicates strong acid. If we do it again, we go to a weak base. We'd expect something sort of in the middle right here, and we do, probably like around a pH of 10. And then finally, a strong base should be up around in the 13, 14 range, and we see this with matching up around with 13. How to use table M. This is really, really important. Okay, so we have methyl orange. Now, this This 3.1 right here, that means from 3.1 to 0, it will be red. From 4.4 up to 14, it's going to be yellow. But in between, we know that red and yellow make orange. So it's just, this is an interesting way of approaching it. Bromthiamyl blue, from 6 and down will be yellow. From 7.6 and up will be blue, but in between it will be green. So if you're ever wondering, like, well, what's the color in between the two? Yeah, yellow and blue make green. Litmus paper, 4.5 to 0 is red, 8.3 and up is blue, and in the middle we have purple. Bromkressel green, 3.8 and down is yellow, 5.4 and up is blue, and in the middle it'll be green. And finally, thymol blue, 8 and down to 0 is going to be all yellow all the time. 9.6 and up is blue. So knowing how to use table M is important to know. All right, let's look at a couple of examples because we're running out of time. Phenolphthalein is pink in an aqueous solution having a pH of. So we go to phenolphthalein. We need something that's 9 and over to be pink, which is why the correct answer here is answer number 4. What is the color of the indicator thymol blue in a solution that has a pH of 11? Okay, so we go over to thymol blue. From 9.6 and up to 14, it's going to be blue. It's going to be blue. So the correct answer here is going to be 2. And now this is an interesting one. 3 samples of the same solution are tested, each with a different indicator. All 3 indicators, bromthiamyl blue, bromkressel green, and thymol blue, appear blue if the pH of the solution is. All right, so I'm going to say bromthiamyl blue. I'm just going to call that BB. From 7.6 and up, it is blue. And I can see that bromthiamyl blue right here. 7.6 and up, it's going to be blue. So for bromkressel green, it is from 5.4 and up, it's going to be blue. And then finally, thymol blue, the last one that we're looking at, thymol blue, 9.6 and up, it will be blue. So in order for all of these to be blue, we need a value that is greater than 9.6, which is why the correct answer here is 4. The correct answer here is 4. All right, final topic for today in the last 5 minutes, titration. A neutralization reaction that is often done in a laboratory is called a titration. In a titration, an acid or base of known concentration is used to neutralize a base or acid of unknown concentration. The volumes used are measured very carefully, and the exact point of neutralization, the endpoint, is marked by an indicator, otherwise known as a color change. This makes it possible to calculate the unknown concentration of the base or acid. Oops. Oh. Okay, at the end point of the titration, the moles of hydrogen ions are equal to the moles of hydroxide ions. So moles of hydrogen must equal moles of hydroxide. That's where we know that we've reached the end point. Table T gives the concentration equation as molarity is equal to moles over liters. We can rewrite this formula as moles is going to equal molarity times liters. Therefore, at the end point, the molarity of the acid times the volume of acid will give you moles of acid. Those two multiplied together, moles of acid. Molarity of base, volume of base will give you moles of base. And you know that you have reached titration if the moles of acid equal the moles of base. So in titration, 20 milliliters of 0.15 molar NaOH solution exactly neutralizes 24 milliliters of an HCl solution. What is the concentration of the HCl solution? All right, the first thing that we should do is write our formula. So MaVa is equal to MbVb. BB. All right, so what do they give us here? They do not, we want the concentration of the HCl. So we're looking for the molarity of our acid. The volume of our acid, it says neutralizes 24 milliliters. I'm going to be a purist here and take my 24 milliliters and convert it over into liters because you should. So 0.024 liters is equal to the molarity of the base, which they give us is 0.150. That's the molarity of the base times the volume of the base, which is 20 milliliters. Again, you should convert it into liters. So 0.02 liters. Because I know some of you could argue, well, if you keep the milliliters the same, won't it give you the same answer? Yeah, it would. But good practice says that you should convert it over into liters. So when we work this out, the molarity of my acid is going to equal 0.125 molar, which is our answer number 1 right here. The other thing to keep in mind really quick is just make sure that your ratio of hydroxide to hydrogen is 1:1, because if it's not, that can really screw you up. Last one for today. A 10 milliliter sample of NaOH is neutralized by 40 milliliters of 0.5 molar HCl. What is the molarity of the NaOH? Okay, so we're going to do MaVa is equal to MbVb. The molarity of my acid is 0.5 molar. The volume of my acid is 0.04 liters. The molarity of my base is what we're solving for. And the volume of my base is 0.01 liters. When I work this out, the molarity of my base should be 2 molar. 2 molar should be our final answer. All right, so what did you learn? Well, I hope you learned a lot or reviewed a lot. Need more help? I'm always available. Feel free to contact me. Thank you so much for participating in this review. I hope it helped. Thanks. Thanks. Bye. Have a great day.